Right now, the next presentation is entitled Advanced Voltage Control Based on Short Time Ahead Voltage Fluctuation Estimation in Distribution System. The talk will be given by Mr. Shinya Yoshizawa, who received the bachelor, master, and PhD degree in electrical engineering from Waseda University, Tokyo, Japan in 2011, 2013, and 2016, respectively. He is a junior researcher at Advanced Collaborative Research Organization for Smart Society in Waseda University. His current research interests include the operation and control of active distributed systems and smart grid. So, Shinya, the floor is yours.
Thank you very much for your kind introduction. Can you hear me?
Yes.
Okay. Good morning. Good afternoon, ladies and gentlemen. My name is Shinya Yoshizawa. I'm assistant professor and adjunct researcher of Waseda University, Tokyo, Japan. Well, I'm going to talk about predictive voltage control scheme of ORTC based on the estimation of short time ahead voltage fluctuation in the distribution system with photovoltaic generations. Okay, here is the outline of my presentation. As you can see, there are 4 parts. First, I gave a short introduction. Second, I describe the proposed control scheme. Then I will talk about some recent experimental simulation results. And finally, I will finish with a brief conclusion. Okay, first, the backgrounds. The number of grid-connected photovoltaic generations, PVs, has been growing and growing. And in Japan, the target installation amount of PVs by 2030 is 64 gigawatt. But however, as you know, there are negative impacts on the distribution system, such as voltage rise and the fluctuations. A problem also have been reported, and they make it difficult to manage distribution voltages within the permissible voltage range. So for future distribution systems, an advanced voltage control scheme will be required. And recently in Japan, sensor measurement units are being introduced to the distribution feeders to measure voltage, current, and power. The use of real-time measurements in the voltage control scheme can mitigate voltage problems, but many issues remain for the practical use. For example, high-speed communication infrastructure is required, and we have to think about the risk of communication failures and the delays. So the objective of this study is to propose an autonomous control of voltage regulators, and especially we propose advanced predictive voltage control to mitigate voltage violations in the distribution system with a large amount of PVs. The proposed control scheme has the following features, but the details are described in the next few slides. Okay. Well, in this part of my presentation, I'd like to tell you about the proposed control scheme. And this slide shows an overview of the proposed control scheme. The proposed scheme is composed of 2 phases, offline phase and online phases. In the offline phase, we approximate the short-time voltage fluctuation distribution by using the press sensor measured voltages. And in the online phases, autonomous type operation is performed to minimize the voltage violation risk in the distribution system by using these approximation results. And okay, in the next few slides, I will describe the more details of these 2 phases. First, I'm going to tell you about how to approximate the short-time voltage fluctuation distribution. Actually, we want to estimate the short time ahead voltage in the distribution system, but it's difficult because the distribution system voltage changes over the time depending on the PV outputs, load demand, and the type of operation of voltage regulators. So we focus on the voltage deviation between between the secondary voltage of over TC and the sensor measure voltages, like this figure. The short-term voltage deviation can be calculated by these equations, and we get this histogram of the short-term voltage fluctuations here. Then we use Gaussian mixture models, and we approximated the short-term voltage fluctuation distributions. And in this presentation, I do not explain the detail of the Gaussian mixture models, but by this process, we obtain the probability density function of short-term change in the voltage deviations. So simply saying, we convert this histogram to the probability density function here by using Gaussian mixture models. Okay. Well, I'm going to tell you about online process, online phases, and how to estimate the short-term ahead voltage distribution here. The short-term ahead voltage distribution can be estimated by using the present secondary voltage of over TC and the probability density function, which is obtained the offline phase. And it is very simple, and it's replaced with the probability density function based on the present voltage of over TC by these equations. The important point here is that we do not directly estimate the node voltages, and we do not need a real-time voltage measurement, just need a secondary voltage of over TC. And this figure represents the short-time ahead voltage distribution based on the present voltage of over TC. So how to change the type of operations? The next step is to calculate the short-time ahead voltage variation risk. The permissible voltage range, permissible voltage limits are given values. So the voltage variation risk can be calculated as a possibility that the voltage values can be maintained within the permissible voltage limits or not. So in this study, we defined voltage safety levels as a probability that the voltage value can be maintained within the permissible voltage range. And it's shown as this shaded area in this figure. And that the type of operation can be done to maximize this voltage safety levels. Okay. And here, the actual type of operation is limited to one. I mean, one up, down, or keep. So the over TC selects the best type of operation to maximize the voltage safety level in the entire distribution system. Let me show you some example of type of operations by using this figure. The blue line is an example of type of operation of over TC, where the top position is changed to the lower top position here. The voltage safety level increases because the voltage distribution is maintained within the permissible voltage range. So in this case, the top-down operation is selected as the best type of operation. Okay, but however, this voltage distribution is based on the past measurements, so that we set the time delay for the type of operation, and only when it is deemed to be necessary, the type of operation is performed. Okay. Well, now I want to go on the simulation case studies. And this slide shows the hardware testbed constructed in the Waseda University. The hardware testbed is scaled down in the laboratory environment, and it is mainly composed of the distribution system simulator called the ANSWER Active Network System, a simulator with energy resources. And this ANSWER is composed of voltage regulators, distribution line devices, and the loader and DEL emulators. And by connecting these devices, we can build any distribution network extending over several kilometers. And by using answer hardware test beds, we built a two-feeder test model, and we tested the proposed method. The proposed method implemented under this ORTC and tested. And for the approximation of the past short-term voltage deviation, 4 node voltages, the first and end node of each feeder are used, N1, N4, N5, and 7. And also the voltage control performance of the proposed control scheme is compared with that of the centralized control method. In the centralized control scheme, the top position of ORTC is to determine to minimize the voltage variation by using the real-time voltage measurement at the same nodes, same 4 nodes. We use monthly measurement data obtained in August, and 25 days data is used for the approximation of the past short-term voltage fluctuation, and 5 days data is used for the evaluation of the control, voltage control performance. And these figures are load and PV profiles used for the evaluation as 5 days data. And here, this slide shows the approximation results with Gaussian mixture models. The negative value represents voltage rise, voltage drops, and the positive value represents voltage rise in the short term. And as you can see, the changes in the voltage deviation at each node varies with time. For example, in the daytime here, it is found that voltage rise and the voltage drop happens in the different nodes at the same time. So by using the conventional voltage control scheme like line drop compensation method or other conventional methods, it's difficult to maintain the proper voltages within the permissible voltage range because this conventional method use only the passing current and voltage at the substation. And this slide shows an example of voltage profiles for day 5 with the proposed and centralized control schemes. As you can see, the voltage violation occurs using the central control scheme. And this is because the voltage control performance depends on the sensor measurement intervals, and the short-term voltage fluctuations are not considered during the type of operation in the central control schemes. On the other hand, the proposed control scheme can prevent the voltage violations compared to the centralized control scheme. And here is a summary of the experimental simulation results. As shown in the table, the number of type operations in the proposed control scheme is increases, but it's not frequent, and voltage violation can be prevented. So experimental results confirmed that the better control performance can be achieved with the proposed control scheme. Okay, well, finally, I'll summarize my presentation. Well, in this study, we propose predictive voltage control scheme based on the short-term ahead voltage fluctuation estimation. And we performed the experimental simulation using our hardware testbeds and compare the voltage control performance of the proposed control scheme with the centralized control scheme. The experimental results confirmed that the better control performance can be achieved with the proposed method. That's all I have to say. Thank you for kind of listening. Yeah.
Thank you very much, Shinya, for your presentation. And now we have time for questions that you can read in the Q&A.
Well,
Shinya, do you have okay, access? Okay.
Oh, sorry.
There are two questions, by the way. I'll let you.
Okay, just sorry for that. Okay. 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 Well, I got the question from the audience. Which factor you taken into account in the object when only the previous execution? Yeah, we did not. Okay, we got the question from the audience. What factor are taken into account in the objective? This only we just consider only the voltage safety levels. This one. Can you see my slide? This we just consider only this voltage safety levels. So we did not consider any objectives. Just like the number of type populations or not. We didn't consider their other objectives. Just only to maximize the voltage safety levels. Okay, and another questions in the central control scheme, can changing the tap position earlier avoid voltage violation? It could be possible, but here, just okay. Well, here, no, here in the centralized control scheme, the real-time the measured voltage can be measured every 10 seconds here. So voltage, so firstly measured voltage and select the tap position to the change the tap to change the tap position, and so how can I say? Well, so this so answer to the questions. This voltage violation can be prevented by updating some parameters of centralized control on so on. But here we just measured every 10 seconds, just minimize the voltage violations in the distribution system. So, okay. What is your definition for the centralized control scheme? Definition of the centralized control scheme is ORTC. No, it's in the definition. Okay, I define the centralized control scheme as the method which is using the real-time measurements. Okay. So this is the number of is that okay? No. Oh. Computing resource is needed for this scheme compared to the. Oh, okay. The another question is how much instrumentation and computing resources are needed for this scheme compared to the centralized control scheme. Actually, we just need not well, how can I say? Just in my method, just for the proposed method, we just need just PC, and actually here we use my laptop PC for the approximation of the short time voltage deviations, fluctuations. So we don't any computing versus is not much higher specification laptop or some PC is not required. Just need some only how can I say? Well, not so much. We don't need any computing resources. Is that okay?
Okay. So maybe still a very quick question before moving to the next presentation. Okay, if not, so thank you very much, Shinya, for your presentation.
Oh, thank you.